We are Team Jet, and today we're presenting Hydrotech's vacuum pump. Our vacuum pump is designed for biological applications, where it's used to dry agar gels and lowers water content. You can see a water reservoir attached on the back. This is a schematic of how the overall system works. There's a Venturi downstream that reduces the pressure at the throat. This creates a pressure gradient that causes water vapor from the gel dryer to flow down to the throat. The rotary vane pump at the bottom pushes water upwards, and this combines with the water vapor and the air from the throat in the Venturi to flow into the water reservoir at the end.
The first step of the vacuum pump's operation is through the rotary vane pump. Here's a picture of our pump with a diagram. Inside the pump, there are 4 vanes mounted to the rotor that move in and out from a spring mechanism so that the vanes maintain contact with the housing as it spins. As seen in the animation, the vanes will continuously rotate, allowing fluid to enter the pump at a smaller area, increase area in the middle, and exit at a smaller area once again. Throughout each cycle, the torque from the motor onto the vanes creates a force exerted from the vanes onto the water. The force applied from the vanes is mostly from the outlet region of the pump, where it is the product of the outlet pressure and exit area. We can use the power, torque, and angular speed relationships to show the pressure of the outlet as a function of radius, angular speed, and power. Nonetheless, to find the physical gauge pressure, it is often easier to use a pump performance curve. From the pump performance curve, we can see that the brake horsepower is linearly proportional to gauge pressure. Since we can look at the pump specifications to find the operating voltage and current output, we can find the brake horsepower. Furthermore, the flow rate doesn't vary since the rotary vane pump is a positive displacement pump and the volume exiting per cycle is constant, and in this case, it is 265 gallons per hour. Using our brake horsepower, we can linearly interpolate to find the gauge pressure, which is 144.27 psi, which is equal to 9.947 bar. To find the outlet pressure of the pump, we need to add the gauge pressure to the inlet pressure, which is only caused by the water column from the reservoir. Assuming an atmospheric pressure and then traversing down the reservoir, we can find the pressure using Bernoulli. This gives us the outlet pressure of 10.980 bars after the rotary vane pump.
The high-pressure fluid from the pump then enters the Venturi, a tube with a neck region that has decreased cross-sectional area, which causes the fluid to speed up and have a decrease in pressure, causing the attached gel dryer fluid to be injected into the neck. This device is mostly illustrated by conservation of mass, where we can assume the fluid maintains a constant density throughout the tube, giving us the relationship between areas and speeds. Thus, if the area decreases in the neck as compared to the inlet, the velocity of the fluid at the neck will have to increase. We can find the flow rate of the pump to be about 265 gallons per hour from the pump specifications document, and since we measure the diameter of the neck and inlet to be 0.00275 meters and 0.01 meters respectively, we can apply the conservation of mass to find the fluid velocities in the Venturi inlet and throat, which is 3.547 meters per second and 46.905 meters per second respectively. While this increase in speed may not have much meaning by itself, it becomes significant once we bring in Bernoulli's equation. With this, we can relate the change in speed throughout the device to the change in pressure. We can safely ignore any changes in height throughout the Venturi, and assuming constant density, we can rearrange the equation to be able to solve for the pressure at the throat using the inlet pressure from the pump calculated earlier, giving us about 7 kilopascals at the neck. This matches the operating pressure of the pump after 10 hours at about 6.5 kilopascals as shown from the document, which meant this is pretty representative of the actual pump performance.
We decided to define the Reynolds number with respect to the Venturi as it plays a central role in the pressure reduction. The length parameter was chosen to be the throat diameter as its value significantly changes the fluid velocity and pressure at the throat. The Reynolds number is known to be around 100,000. Our system is in transitional flow. We assume that there was no turbulence and viscous effects, but since it is between laminar and turbulent flow, in future analysis, perhaps these effects should be taken into account. Decreasing the diameter by a factor would raise the fluid velocity to that factor squared by conservation of mass. This will lead to a greater Reynolds number and hence greater turbulent effects and less viscous losses. There will be a thicker boundary layer on the surface of the Venturi, which causes greater heating effects for faster flows. Meanwhile, increasing the diameter further decreases the Reynolds number. It will decrease turbulent effects but increase viscous losses, minimizing the gauge pressure that is allowed for the pump and the flow rate in the vacuum pump overall, making the machine overall less efficient and time-consuming. So for the optimum construction of a vacuum pump, one has to take into account a balance of these turbulent and viscous effects.
Here's some behind-the-scene photos of our dissection, and additionally, one funny incident was that Kirby actually broke one of our Venturis, shown on the right, but thankfully we had an extra to break apart and analyze. Thanks so much for watching our video.